Hello everyone. Now before we move on to eigenvalue problems, I thought this would be a good time to have a brief review on matrices and on important properties of matrices, which will come handy when we solve eigenvalue problems using all the concepts of vector spaces that we have learned so far. So what is a matrix? A matrix is a rectangular array of numbers or functions which are enclosed in brackets. So we all know about what this is. Some general concepts and notations that we'll use. The elements of a matrix are denoted in general by writing the a general entry inside brackets. So if I have a matrix A, then the any element of the matrix is given as A, J, K. So J and K, these are two subscripts. J will go over the number of rows and K will go over the number of columns. So we put this general element, we put this inside the square brackets, so that gives us, that is generally how we represent a matrix. So when I say an M cross N matrix, it means a matrix which has got M number of rows and N number of columns. In general, this is how a matrix looks like. So I could just call it as a matrix A, or I could represent this inside bracket a general element A, J, K. And what this means is, if I want to expand it, so I have A11, A12 and so on all the way till A1n. Likewise, in the second row we have A21, A22 and so on all the way till A2n, and so on, AM1, M2 and so on. Okay, so here we have M number of rows. So we have M number of rows. So you can see here number of rows. This is the number of rows. The first index is the number of rows. So 1, 2, 3, 4 all the way till M. And the number of columns, there are N columns. The second index is the number of columns. So 1, 2, 3, 4 all the way till N. So this is a M cross N matrix. So if I say A, I, J, so but here I stands for the row number, I stands for the row number, and J stands for the column number. If M is equal to N, then that's a special kind of a matrix. We call it as a square matrix, which is what we are interested in over here. The main diagonal or the principal diagonal of a square matrix are those which contain the entry where the row index and the column index, they are the same. So if, for example, if I consider a 3 cross 3 matrix, it's a square matrix because here the number of rows and the number of columns are the same. So the elements are going to be A11, A12, A13. This is the A13. This is the first row. The second row will be A21, A22, A23, and the third row will be A31, A32, and A33. And so what are the diagonals? Diagonals are those in which the index of the rows and the index of the columns are the same. So here A11, both the indices are same. A22, these indices are also same, and this index is also same. So this becomes the principal diagonal or the main diagonal of this square matrix. Okay, so a vector, what is a vector? Vector is also a matrix. So any matrix which has got only one row, either one row or one column, that's known as a vector. So if it has got only one row, then as a row vector. If it has got only one column, that is known as a column vector. So row vector, when I say row vector, we are going to have a vector which looks like this. So row vector means a vector which looks like something like this. So we have, certain number of elements over here, and a column vector looks like this. We are having columns which are arranged. We are going to have elements which is arranged in a column. So that's your row vector and a column vector. So essentially, even though we call it as a vector, but actually it's nothing but a matrix itself. So these are represented as A, J. So here we don't really require both the indices. Because it's understood. Okay, it's understood because if there's only one index, it's understood. The other one, there's only one possibility, either is one row or one column. Then the transposition of a matrix. So if I have a M cross N matrix, let's call this as A, then its transpose, that is AT or A prime, is the N cross N matrix, in N cross M matrix, in which the first row of A is its first column. So the original matrix was A, you take the first row of that matrix A, and with that you construct the first column of another matrix. That another matrix will be the transpose, and so on. So here we can see A is this matrix. So we have, these are the elements of the first row. So we have these are the elements of the first row, and these elements you see A11, A12, A all the way till A1n. This becomes the first column. Likewise, if I take, let's say, the second row, so we have the second row, these are the elements of the second row. So these elements of the second row, you can see here it has become the elements of the second column in this matrix. So this and this is these are transpose of each other. These two matrices, they are transposes of each other. So when I say transposition, this is what we need to do. You have to swap the rows and the columns. A matrix is symmetric if A prime, the transpose of a matrix, is equal to the matrix itself. Okay, so if a matrix, if it's the same thing, so for instance, if I have a matrix like this, 5 1 3 2 0 6 7 9 1, this is a matrix A, this is a matrix A. Then if I take the transpose of this matrix, A transpose, so this will be, first row is 5 1 3, so it will become the first column, so 5 1 3. Next is 2 0 6, that will become the second column, 2 0 6. Then we have 7 9 1, and obviously we can see here that these two are not the same. Okay, these two are not the same. Here there is a 2, there is a 1 here, here there is a 1, there is a 2 here. So these two matrices are not the same. So this is not a symmetric. So this is not symmetric. So when will this be symmetric? When these two here and here, if it is the same. So do we have a 1 there? If we also have a 1 here, okay, and here we have a 3 here, or a 7, if suppose this is a 7, if this is a 7, so here on both sides we have 9 and 6, so let's say this is 6. Okay, now in this case, if you take the transpose, it will remain exactly the same. So we'll have a 1 here, we'll have a 7 here, we also have a 7 here, and we have a 6 here. So when you take the transpose, 5 1 7, so we have 5 1 7, next is 1 0 6, so 1 0 6, then 7 6 1, so 7 6 1. So this is exactly the same. So now this becomes a symmetric matrix. Okay, and suppose I have something like this. Okay, this is a symmetric matrix, this becomes a symmetric matrix now. But suppose I have something like this, 5 minus 1, okay, then 7, then minus 6. Okay, so now if I take the transpose, then this is going to become minus, sorry, so we have 1 plus 1 minus 1, and then I think we need a minus here. Yeah, so we have 5 minus 1 minus 7, 5 minus 1 minus 7, then 1 0 6, so 1 0 6 comes here, 7 minus 6 1. Okay, so that means over here what happens is A transpose is the negative of A. A transpose is the negative of A. So in that case, we say that this is skew symmetric. Okay, so this is a skew symmetric matrix. Moving forward, multiplication of matrices. Then suppose I am having two matrices A and B. Okay, so the suppose I have one matrix A, another matrix B, and I want to find out the product of these two matrices. So A is a M cross N matrix, okay, and B is an R cross P matrix. So we have two matrices. Let me write down here. So I'm having two matrices A, a matrix A here, and another matrix B here, and this matrix A, it's a M cross N matrix, and this matrix B, it's a R cross P matrix. An R cross P matrix. Then if I want to take the product of these two, that is, if I want to find out A, B, the product of these two, then this product is it's possible to multiply these two matrices only if the number of columns in the first matrix, the number of columns in the first matrix, and the number of rows in the second matrix, if these two are the same. Okay, only if these two are the same, the number of columns of the first matrix and the number of rows in the second matrix, if only these two are the same, then only we can find the product of these two matrices. So then C is defined as, then this is going to become, so we have M cross N matrix and R cross P, N is equal to R. That means this matrix, this is going to be, what will be the dimensions of this matrix? This is a M cross P. This will be an M cross P matrix, and its elements are given in this way. So now this is, I mean, for till school level, this is important that you remember this formula. It's much easier to remember this visually. So this is what happens here. So I have a matrix A and I have a matrix B. So you take, let's say, the jth row. This is the jth row, and this is the kth column, the jth row and the kth column. Then you multiply them element wise. You multiply the jth row and the kth column element wise, and when you multiply them element wise and add them all together, then that is going to give us the jk, the element jk of the product matrix. Now you know why this condition is required, this condition that R must be equal to N, because this one is, it has got M rows and N columns, it's got M rows and N columns. So that means this one has N number of elements. Okay, this one has got N number of, this row has got N number of elements, and here we have N rows and P columns. That means here also we have N number of elements. So you can multiply this row and this column, you can multiply them only if the number of elements here and the number of elements here will be same. So that's why we have this particular requirement. That's why we have this requirement that the number of columns in the first matrix and the number of rows in the second matrix, they must be equal. And once you do that, this multiplied by this, okay, the element wise, add them together, that is going to give us the jk element of the product matrix. So in fact, I have I have prepared a spreadsheet which will help me to quickly calculate this. So let's say I have a matrix A and a matrix B. Then you can calculate, let's say I have matrix A is 1, 3, minus 5, and then 4, 0, 6, then 9, minus 7, 2. Okay, this is matrix A. Matrix B is 6, 3, minus 1, minus 2, minus 2, minus 3, 1, 0, 8, 9, 4. Okay, so these are two matrices. This is matrix A and this is matrix B. Okay, the product of these two. So this is the product AB. This is AB. When you multiply A with B, that is the first matrix is A and the second matrix is B. So this is the result. This is the result that you get. So you can see here, very clearly that what we are doing is we are multiplying the first row and the first column. We are multiplying, that becomes the first 1, 1. Then for this one, what you do is you multiply the first row with the second column, 1, 2. So this is element 1, 2. Similarly over here, element 1, 3, first row and the third column, multiply them, this is what you get. Similarly over here, second row, second column, third row, third column. Likewise, let's say here, this is BA, you are multiplying B with A. B is the first matrix and A is the second matrix. So B 2, 3, second row, third column, 2, 3. So second row here and the third column here, multiply them and you get this. Okay, so this is your matrix multiplication. So first thing that immediately strikes you is, you see the matrix multiplication is not commutative. That is, AB and BA, they are not the same. Okay, so this is one property of multiplication of matrix. So matrix multiplication in general, it is not commutative. AB need not be equal to BA. If AB is equal to 0, that does not imply A is equal to 0 or B is equal to 0 or BA is equal to 0. Okay, some examples are shown here. 1, 2, 2, this is definitely not a 0 matrix. Minus 1, minus 1, minus 1, 1, 1, minus 1. If you multiply these two, you'll get 0, 0. It's got the 0 matrix. Similarly, multiply this with this, you'll get this one. Okay. So over here, you're multiplying A with B and you're getting the result 0. But A is not 0, B is also not 0. Okay. AC equal to AD does not necessarily imply C equals D. So this is A and this is C. Okay. Let me write this down here. So this is matrix A and this is matrix C. And again you can see here this is the same matrix, this is A and this is the matrix D. In both the cases the result is the same, but are these two matrices the same? These two matrices are not the same, so we cannot really imply that if AC is equal to AD, we cannot simply cancel out. Algebraically this is what we do, you cancel out A and A here and we conclude that C is equal to D, but you can't do that when you are working with matrices. Then these are some other properties. Okay, so some distributive that we have, and associative and distributive properties. You can verify each of these. You can take some matrices and you can verify them for yourself. The transpose of a product. So suppose I have two matrices and I take the product of these two matrices, and then after taking the product, if I take the transpose, that is the same as, suppose I am having A is the first matrix and B is the second matrix. Okay, I am multiplying them A and B, and then I am taking the transpose. That is the same as first taking the transpose of the second matrix here, that is B transpose A transpose. Okay, the order gets changed. So if there is a transposition outside and you want to open up this bracket, then the transposition goes inside, and when the transposition goes inside, then the order will change. A B, it will become B A, B transpose A transpose. So this is a very important result for us to remember. Then there are some special matrices. One is known as an upper triangular matrix, a square matrix that can have non-zero entries only on or above the main diagonal. You can see it for yourself here. So this is the main diagonal, right? This is the main diagonal, and you can see here we have non-zero entries over here. This is a zero entry. Similarly over here also. Okay, so you can see here we have non-zero entries over here. Likewise, we have non-zero entries over here. So this kind of a matrix is known as an upper triangular matrix. So we have non-zero entries on or above the main diagonal. So that's an upper triangular matrix. Likewise, you could have a lower triangular matrix. In the lower triangular matrix, you will have non-zero entries only on or below the main diagonal. So you can see here, so we have, this is the main diagonal, okay, and then we have non-zero entries over here. Similarly, we have non-zero entries over here and non-zero entries over here in this 4x4 matrix. But remember, when these all these special matrices that we're talking about, that is applicable only for square matrices. Okay, so that's a upper triangular and a lower triangular matrix. Moving on, a diagonal matrix. A diagonal matrix is a matrix which can have non-zero entries only in the main diagonal, everything else, all other elements, they are zeros. So you see, this is the main diagonal, we have non-zero entries. Similarly over here, this is the main diagonal, we have non-zero entries, everything else is zero. Then similarly over here, this is the main diagonal, we have non-zero entries over here only, everything else is zero. A scalar matrix, if all the entries of a diagonal matrix, so this is a diagonal matrix, okay, so if all the entries of a diagonal matrix are equal, say K, we call this S as a scalar matrix. So matrices like, okay, 7 7 7 0 0 0 0 0. So this is a scalar matrix, this is a scalar matrix. Okay, then we have a special kind of a scalar matrix which is known as an identity matrix. How is it special? It's special because all this scalar, right, which exists, the same scalar which exists along the main diagonal, if that scalar happens to be 1, if that happens to be 1, so 1 1 1, so we have zeros everywhere else, we have zeros, then this becomes what we call as an identity matrix. An identity matrix. Okay, so identity matrices are really important because they perform the same function as 1 in algebra. 1, the number 1, unit, okay, unity, whatever role it performs, the same thing, it performs the same thing in matrix algebra. Okay, so AI, if I multiply a matrix A with I, so whether I post multiply or pre multiply, this is post multiplication, this is pre multiplication, in both the cases the result will be same, it leaves the matrix unchanged. So multiplying a matrix with a scalar matrix multiplying a matrix with a scalar matrix, the result is going to be commutative. Okay, so I did not when we talked about the multiplication of matrices, I said the result need not be commutative. That means it can be commutative. It will be commutative if one of the matrices happens to be a scalar matrix. Then in that case, the product of these two matrices is going to be commutative. And if suppose in addition, if the scalar matrix happens to be an identity matrix, then the product not only is it commutative, but it is same as the other matrix. Okay, so that is what is known as an identity matrix. Then determinants. The nth order determinant is an expression associated with cross n matrix A, and it is denoted in this way. Either you put two vertical bars or you write det, determinant A. So it is an expression which is associated with this matrix. So for any two matrices A and B, if I take the product, okay, and I find the determinant, it really does not matter. The order does not matter. Whether it's A, B or B, A does not matter. You might as well just take the determinant of A and multiply with the determinant of B. Second order determinant. This is how you find out the second order. So second order determinant means nth order is associated with n cross n. This is important. So when I say nth order determinant, that means we are talking about a n cross n matrix. So when I say second order determinant, that means we are talking about a 2 cross 2 matrix. So if you have a 2 cross 2 matrix, this is what a determinant looks like. So instead of trying to remember this formula, just remember this one. So you multiply these two and then minus multiply this one. Okay, multiply this, let me write it better, multiply these two, okay, then subtract, from that you subtract the product of these two, this into this minus this into this. So if you remember this structure, then it will be easy to remember second order determinant. So second order determinant is most basic. Then for third order determinant, it's a little bit complicated. So it's slightly more complicated. So what you do is you can open up using either any row or any column. Usually you should always look for rows which are having the maximum number of zeros, because then it becomes easier. So let's say if this is 0 and this is 0, then automatically this term and this term will be 0. So finding the determinant will be easy. So always when you are trying to find out the determinant, always look for rows which have got maximum number of zeros. So let's say we open this using the first row. So what you do is you take A11, take the first element, okay, and when you take the first element, then you delete the row and the column in which contains that element, and what is left behind, that is known as a cofactor. Sorry, I think it's called the minor. Let me just check. Yes, this is known as a minor, not the cofactor. So you take the minor. So this is known as a minor. That means I delete. I'm looking. This is the element that I'm considering, A11. So which is the row and which is the column that contains A11? You delete that. Then what is left behind is going to be a 2 cross 2 matrix. From a 3 cross 3 matrix, we are constructing a 2 cross 2 matrix. So this 2 cross 2 matrix is known as a minor. Find out the now this 2 cross 2 matrix, you can find out the determinant very easily. So that will be simply A22 A33 minus A32 A23. Okay, so A11 into determinant of this. Then next you take the next element. The next element will be A12. We're opening up with this. We're opening with respect to the first row. Next you take A12. So when you take A12, that means we have to delete the first row and the second column. So what is left behind is this one, 1 2 3 4. Then A1, sorry, I think, yes, I had opened up over here. I had opened up with respect to the first column, but we might as well do it like this. So instead of this, we might do it as A12, and what is left behind is this matrix, A21, A21, A23, A23, and A31, A31, and A33. This is what is left. Now where did this minus sign come from? This minus sign comes from because we are from the minor we construct what is known as a cofactor. So what you do in a cofactor is we have to multiply minus 1. Okay, how do you get the cofactor? Minus 1 to the power the row number and the column number. So here, which is the row number? The row number is 1 and the column number is 2, right? The row number is the first row and the second column. Row number is 1 and column number is 2. So minus 1 to the power 1 plus 2, which is minus 1 to the power 3. So minus 1 to the power 3 will give us a minus 1. Similarly, over here, minus 1 to the power 3 plus 1, okay, or minus 1 to the power 1 plus 3. 1 plus 3 is 4. So minus 1 to the power 4 is plus 1. So we get a plus sign here. Easier way to remember would be every position will have a plus, alternating plus or minus sign. So we have a plus sign, minus sign, and a plus sign. Similarly, here we'll have a minus, a plus, and a minus, and plus, minus, plus. So if you remember these signs, then it's very easy just to pick up these signs and then perform this operation. Okay, so that's how you find out the determinant of a third, or that's how you find out the third order determinant. Okay, so for in general, for nth order determinant, we find out the minor first, okay, then the cofactor. Okay, how you get the cofactor is just from with the minor you multiply minus 1 to the power j plus k. It is a jkth element, so j plus the row number and the column number, add them together, raise minus 1 to that number. Then an nth order determinant is obtained in this way. So j can be anything, 1, 2, 3 all the way till n. So it can be any row or any column. So either of these two you can use to find out the nth order determinant. Now the same thing here I am writing in terms of cofactors, but you could also write this in terms of minors like this. So I am sure this is one thing that this is one expression, this is the formula that you would have probably learned in your mathematics course in your class 11 probably. Now the rank of a matrix. The rank of a matrix is the maximum number of linearly independent row vectors of a matrix. This is known as the rank of a matrix. So for example, let's say I am having this matrix. Okay, so this is the matrix. So you can, what are the row vectors? So this is one row, so 3 0 2 2, this is one row. Then minus 6 42 24 54, this is another row. And this one 21 minus 21 0 and minus 15, this is another row. Now if you examine this, you can find out that a1 and a2 are linearly independent. That is, there is a 0 here, right? There is no way by which you can get a1 from a2. You cannot multiply anything, because no matter what number you multiply, no matter what scalar you multiply to a2, you can never get a 0 over here. So there is no, and also one more thing is these two are the same, but here 24 and 54, they are not the same. Okay, so there is no way by which, also here there is a minus sign, and here we have these two quantities are plus, but here all of them are positive. So there is no way by which I can multiply, I can find the scalar by multiplying the scalar with a2, I can get a1. There is no way I can do that. Okay, so a1 and a2, they are linearly independent, but a3 is not. A3 is not linearly independent of a1 and a2, because you can verify this for yourself. If I multiply a1 with 6 and a2 if I multiply with minus half, and then I add these two together, then I'll get a3, or 6a1 minus half a2 minus a3 is equal to 0. So which means, this implies that a3 is equal to 6a1 minus half a2. a3 is this. So that means a3 is a linear combination of a1 a2. So that means a3 is linearly dependent, a3 is linearly dependent on a1 and a2. Okay, so in this matrix, even though there are three rows, but out of these 3 rows, 2 rows are linearly independent. Only 2 rows are linearly independent, that is row number 1 and row number 2. So therefore for this matrix, its rank will be equal to 2. That will be its rank. Okay, so this is how you find out the rank of a matrix. Okay, so here in this case, rank is equal to 2. So there are some theorems. Rank of a matrix A equals the maximum number of linearly independent column vectors. So rank of A is equal to rank of A transpose. Then another theorem, an n cross n matrix A has a rank n if and only if its determinant is non-zero. Okay, if I have an n cross n matrix, let's say a 3 cross 3 matrix, its rank will be n, that is all the 3 rows will be linearly independent if and only if its determinant is not equal to 0. If suppose you're asked a question, okay, you're asked a question whether examine whether a matrix is has got linearly independent row column vectors or not. How do you examine? Just find out its determinant. If the determinant happens to be 0, then you can say that it does not have linearly independent rows and columns. That means its rank is definitely not equal to n. Okay, so this is a second theorem. Okay, so given n cross n matrix A, there is something called as an inverse of a matrix. There is something called an inverse of a matrix. We are interested in finding the inverse of a matrix. When we can talk about inverse of a matrix only for square matrices, and for all square matrices we need not always have an inverse. Okay, so if I have an n cross n matrix A, its inverse, if it exists, it is denoted by A minus 1, A to the power minus 1. So A is a matrix. A will have an inverse. If its inverse exists, that inverse we will denote it as A to the power minus 1. Okay, so this A to the power minus 1, this will be another n cross n matrix. So A is a matrix, it's an n cross n matrix, and A inverse will also be an n cross n matrix. But then this inverse, it should exist. Okay, the inverse, it should exist. If the inverse exists, then what is this inverse? The inverse is another matrix such that if you multiply the matrix with its inverse or the inverse with the matrix itself, the result will be the identity matrix. Okay, so that is known as an inverse of a matrix. So if suppose a matrix, the inverse of a matrix exists, then such a matrix is known as a non-singular matrix. A non-singular matrix means a matrix whose inverse exists. But if no inverse of such of a matrix exists, then it is known as a singular matrix. So singular or non-singular, these are two terms. We can use it to identify whether inverse exists or not. Okay, non-singular means the non-singular matrix means inverse does not, its inverse exists. Singular matrix means its inverse does not exist. Then if a matrix is non-singular, then its inverse is unique. So if I have a matrix A and it is non-singular, that means its inverse exists, then that inverse must be unique. That is, it is not possible to find another matrix. It is not possible to find another matrix such that that matrix and that matrix is another inverse of the given matrix. So it's not possible this way. So suppose I am having a matrix A. Okay, suppose I have a matrix A, and then this matrix, I say that there is another matrix B such that this B is the inverse of A. That is, there exists B such that AB is equal to the identity matrix. Okay, and let's say I say that there is another matrix C. There is another matrix C such that, okay, I should not say IE, it's such that AC is also equal to the identity matrix. So this implies this matrix B must be equal to matrix C. This can be very easily proved. So I leave this to you to try it out for yourself. So now there is a theorem. The inverse of an n cross n matrix exists if and only if the rank of that matrix is n. The inverse of a matrix exists if and only if its rank is equal to n. Okay, if I have an n cross n matrix and if its rank is equal to n. So what do you mean by rank of a matrix is n? That means all the rows or all the columns. Okay, so I have a matrix, let's say this is the matrix A. Okay, let's say we have 1 2 3 1 2 3. It's a 3 cross 3 matrix. Let's say 3 cross 3 matrix. So you take the first row, second row, third row, any of these 3 rows, all of them are linearly independent. Or if you take the first column, second column and third column, any of these, either you take rows or you take columns, they are going to be linearly independent. The 3 rows, they are linearly independent of each other. The 3 columns, they are linearly independent of each other. Okay, then we said that the rank of this 3 cross 3 matrix is 3. Okay, so the first theorem, what it says is the inverse of an n cross n matrix exists if and only if the rank is equal to n. For a 3 cross 3 matrix, if its rank is also equal to 3, then the inverse of that matrix exists. Then from the above theorem this theorem number 2, which was on the previous slide, let me go back to the previous slide. Theorem number 2, an n cross n matrix has a rank n if and only if the determinant of A is not equal to 0. Let me write this down here. N cross n matrix A has rank equal to n if and only if determinant of this matrix is not equal to 0. So this was the theorem, and then over here we have this theorem number 1. Okay, so from this particular theorem, from this particular theorem and from this theorem, so what does this theorem say? The inverse exists if and only if rank is n. Okay, and when is the rank equal to n? When the determinant is not 0. So from the two theorems, from these two theorems, the logic says that matrix, the inverse of a matrix exists if and only if the determinant is non-zero. Okay, and n cross n matrix is non-singular, that is, it has got its inverse exists if and only if A is the determinant of this matrix is non-zero. Now the inverse of a non-singular matrix can be obtained using the Gauss-Jordan elimination method, which you will be learning in your this computer oriented numerical methods, but I will show you another method, a very elementary method. So let me just go to the slide. So let's say I want to invert this matrix. Okay, I want to invert this matrix. So there are certain steps that you can follow, and when you follow these steps, then this is for a 3 cross 3 matrix. Okay, so I'm going to concentrate here on a 3 cross 3 matrix. Okay, just example matrix I have taken 0 1 2 1 2 3 3 1 1. So this is the matrix that I have taken. So there are certain steps that you can follow, and using these steps you can easily find out its inverse. Okay, so let me write down these steps. So first step is to compute the determinant. Okay, first step is to compute the determinant. So let's go ahead and compute the determinant of this matrix. Okay, determinant of this matrix. So let's say we call this matrix as matrix A. This is matrix A. Okay, I want to find out what is the determinant of matrix A. Okay, so how do you go about doing that? We need to choose either any row or any column. So in this case, the best row or the best column to choose will be the first row, because the first row or the first column, because the first row, it has got a 0 here. Always look for the row or the column which has got maximum number of zeros. So we are going to choose the first row, let's say. So choosing the first row, what we have is whichever is a 0, that we don't have to worry about. We just need to worry about this one. So the other two elements, so we'll have, then of course we'll have to take into account the sign which I was talking about when we were finding the cofactors. Okay, so when we're finding the cofactors, the sign that is associated with these places, so we have a plus sign associated, a minus sign, another plus sign which is associated. Similarly, minus, plus, minus, but we are not going to use that. So there's a minus sign which is associated over here. So we'll have minus 1, minus 1. Once we have taken minus 1, then this element, that means we need to delete this row and delete this column. Then whatever is left behind, what is left behind is this one. So that will be the determinant of 1 3 3 1. Okay, and then next one will be, we'll choose this one. Okay, so we'll have plus 2. So plus 2, this element is 2. Then this is the minor. Okay, taking into account the sign, so we'll have plus sign, so that will give us the cofactor. So 1, so we have to find out the determinant of this one. So 1 2 3 1. Okay, now once that is done, then that is, rest of it is very easy. So minus 1. So now how do you compute this? We compute this using this scheme, right? Okay, do it like this. That means minus 1 times 1 times 1 is 1, minus 3 times 3 is 9. Okay, then plus 2, again the same thing. Oops. Okay, putting this over here, so 2, so you have 1 times 1 is 1, minus 3 times 2 is 6. Okay, so this is going to give us, have 1 minus 9 is minus 8, minus 8 and minus 1 is going to give us plus 8, and then we have minus 5 here, and 1 minus 6 is minus 5, minus 5 into 2 is minus 10. So this will give us the determinant to be equal to minus 2. So determinant of this, determinant of A, you could also write it this way, the determinant of A is equal to minus 2. So first step is compute the determinant. Once you have computed the determinant, then we can go to the next step. What is the next step? The next step is replicate the first two columns to the right. Replicate the first two columns to the right. So what I mean by that is this: replicating the first two columns to the right. What I mean by that is something like this. So this is the matrix. Okay, this is my original matrix. So I want to replicate the first two columns. The first two columns, that means this column. Let me highlight this first column. This is the first column. Let me use a different color. This is the first column, and this is the second column. Okay, so we have to replicate these two columns to the right side. Okay, we have to replicate these two columns to the right side. So this is the first column. So let's replicate this. So how we replicate this? Just copy this and stick it onto the right side. Okay, so we have replicated this. Next we want to replicate the second column. Okay, the way to replicate the second column will be, again, just make a copy of this and place it to the right side. Okay, all right, so that's your second step. Okay, next step is replicate the first two rows to the bottom. In a similar way, take the first two rows and replicate it at the bottom. Okay, so this is the first row. Okay, ungroup this. Okay, so take the first two rows. This is the first row. Make a copy of this and place it at the bottom. Then take the second row, make a copy of this and place it right at the bottom. Okay, okay, so this is what you do. So replicate the first two rows to the right and replicate, then whatever is the resulting matrix, that replicate the first two columns to the right and then replicate the first two rows to the bottom. So these two steps, at the end of these two steps, from a 3 cross 3 matrix, from the original 3 cross 3 matrix, you should end up with a 5 cross 5 matrix. Okay, you should end up with a 5 cross 5 matrix. Okay, because we are replicating 2 rows to the right and 2 rows to the bottom, so it will become a 5 cross 5 matrix. Okay, so now what you do is, from this resulting matrix, you delete the first row and the first column. From this one, you delete the first row and column. Okay, like so. This is the first and the first column. This is the first row and the first column. We'll just delete this off. So once we have deleted this, we have something like a minor. So from a 5 cross 5 matrix, we'll get a 4 cross 4 matrix. Okay, so this should lead us, this step, it should lead us from a 5 cross 5 matrix. It should take us to a 4 cross 4 matrix. Okay. Now once we have got this 4 cross 4 matrix, now what we do is we construct a matrix from the determinant of every 2 cross 2 submatrix. So let me just note it down. That will be step number 5. Construct a matrix. Construct a 3 cross 3 matrix. 3 cross 3 matrix from the determinants of every 2 cross 2 submatrix. Let me show you how. So let's say I take the first submatrix, that is this submatrix. Let me highlight this submatrix. Let's say I take this submatrix. Okay, so we need to find out the determinant of this submatrix. Okay, so how do you find out a determinant? We again follow this rule, right? Let me just put this aside for the time being. We want to find out the determinant of this one, so for that we use this rule. Go from here to here and from here to here. Okay, so we want to find out this submatrix, determinant of this particular submatrix. So what you do is you go like this. So 2 times 1 is 2. 2 times 1 is 2. Okay, 2 times 1 is 2 minus 1 times 3 is 3. So 2 minus 3 is minus 1. 2 minus 3 is minus 1. Okay, once this is done, then we'll move on to the next submatrix. This is the submatrix. So here also we'll find out the determinant. Okay, so the determinant will be 3 times 3 is 9 minus 1 times 1 is 1. So 9 minus 1 is going to give us 8. Okay, again take this submatrix. 1 times 1 is 1. 1 times 1 is 1, and 3 times 2 is minus 3 times 2 is 6. Okay, so 1 minus 6 is going to give us minus 5. It's going to give us minus 5 here. Do the same thing for this submatrix. Same rule. So we'll have 1 times 2 is 2. 1 times 2 is 2 minus 1 times 1 is 1. So 2 minus 1 is going to give us 1. Again, for this submatrix, 1 times 0 is 0, right? And then minus 0 minus 0 minus 2 times 3 is 6. So this is going to give us minus 6. Proceed further. this submatrix. 3 times 1 is 3 and anyway 0, so 3 times 1 is 3. Next one is this. 1 times 3 is 3, minus 1 times 3 is 3, minus 2 times 2 is 4. So that's going to give us 3 minus 4 is minus 1. Next one, 2 times 1 is 2, 2 times 1 is 2, minus 0 again. Then here, oops, the last submatrix 0 and minus 1, so we'll get a 1 here. Okay, so this is how we construct. Okay, so we constructed a matrix, a 3 cross 3 matrix. Again, in this step, construct a 3 cross 3 submatrix. That means in this step we'll go from a 4 cross 4 matrix. So here from 3 cross 3 matrix we went to a 5 cross 5 matrix. By deleting one row and one column, from 5 cross 5 we got to a 4 cross 4 matrix, and again from this 4 cross 4 matrix we again go back to a 3 cross 3 matrix. Okay. Okay, so that is step number 5. Once we are here, after this, divide by the determinant, Okay, so divide every element with the determinant. And which is the determinant? Determinant is minus 2. So every element will divide by the determinant. It is, oops, so these are the elements. Okay, so every element will divide by the determinant. Determinant is minus 2, so divide by minus 2 everywhere. Okay, so we divide by minus 2. So minus 1 divided by minus 1 divided by minus 2 is 0.5. Then 8 divided by minus 2 is minus 4. 8 divided by minus 4. Then minus 5 divided by minus 2 is 2.5. Then 1 divided by minus 2 is minus 0.5. Then minus 6 divided by minus 2 is 3. Then 3 divided by minus 2 is minus 1.5. Minus 1 divided by minus 2 is 0.5. And finally 2 divided by minus 2. 2 divided by minus 2 is minus 1. And lastly we have this. Minus 1 by minus 2 is 0.5. I hope I am right. If I've done this correctly, the sign should get reversed. So we have a minus, it becomes plus. We have a plus here, it becomes minus. Minus becomes plus. Plus becomes minus. Minus becomes plus. Then again minus becomes plus here. Sorry, plus becomes minus here. Minus goes to plus. Plus goes to minus. Minus goes to plus again. So this is what we get. Okay. Once we have got this, then we go to the last step. Okay, the last step is find its transpose. Step number 7. Its transpose is the required inverse. Its transpose is the required inverse. So all you need to do is find out its transpose. This one's transpose, that will be the inverse that we are looking for. So it means what will be its transpose? So we have 0.5 minus 4, 2.5. So 0.5 minus 4 will come over here, minus 4, and 2.5. Then we have minus 0.5, minus 0.5. Then we have 3 and minus 1.5. And finally we have 0.5 minus 1 and 0.5. Okay, so this will be the inverse that we are looking for, the given matrix. Okay, this matrix A, its inverse will be this. Okay, so these are the steps that we can follow. This is a procedure that we can follow to find out the inverse. In fact, we can just try this out. I had shown you a spreadsheet where I can calculate the inverse of a matrix. So so here it was. Let's try this out. 0, 1, 2. Let's do that here. 0, 1, 2. So we have 0, 1, 2, 0, 1, 2, then 1, 2, 3, 1, 1, 2, 3, 1, 2, 3, 3, 1, 1, 3, 1, 3, 1, 1. Okay, and the other matrix that we got here was 0.5 minus 0.5 and 0.5. The other one was 0.5 minus 0.5, 0.5, 0.5 minus 0.5, 0.5, minus 4, 3, minus 1, minus 4, 3, minus 1, minus 4 here, minus 4, 3, and what was it? It was minus 4, 3, minus 1. Okay, and the last one will be 2.5 minus 1.5, 0.5, 2.5 minus 1.5 and 0.5, minus 1.5 and 0.5. Okay, and because it's an inverse, and we know for an inverse what should happen, a matrix if you post multiply with its inverse, or if you pre multiply with its inverse, the result will be the identity matrix. And we can see here in both the cases this is the identity matrix, and here also is the identity matrix. Okay, so that was basically a brief review of matrices. In the next class we will have a look at eigenvalue problems. Thank you.